Numberphile released a video some 3 weeks ago related to the breadth first search algorithm. It was animated very beautifully, and I believe it was done in Mathematica. I wanted to do the same thing in JavaScript and see how it goes. Let's begin. Hey buddy.
Hey RK, what's up?
Other
than the Chennai temperature.
The Chennai temperature.
Oh right. Gosh.
I think we've spoken about it like 10 times today.
It
right?
was so hot.
The middle of October, of all the things. Alright, so you remember that Numberphile video we saw the other day?
Yeah, you showed me that.
Breadth first search, and then he sort of made a lightning simulation.
Right. And the end, it just goes up to the starting point.
To the starting point.
Yeah.
So I wanted to do something like that.
Okay.
In lieu of, basically we've not received any suggestions from our viewers. So I've it was released only 3 weeks ago, fortunately. So that gave me an idea.
So they do it in Mathematica.
They do in Mathematica.
And you going to do it obviously in your
JavaScript.
Canvas and JavaScript.
HTML5 and JavaScript and everything.
Perfect. Okay.
Right?
Yeah.
Alright. So I'll just explain the breadth first search algorithm because I think that's important to the entire video. That ties the entire video together.
Sure.
So let's go to the presentation. Alright, Ravi. So this is a graph tree that shows the connection between a set of friends. Because you're my best friend, I've put you on top. Right? Technically speaking, there is no begin or end to a graph tree. Yeah. At least as far as the breadth first search is concerned.
Correct.
You might want to sort of get a connection between, let's say, Ani over here and Lax. How will that connection go, or things like that. Alright. So, but just for the sake of convenience and the sake and
there is
there is a hierarchy to it. So let's say Ravi, let's say Manu works in some sort of YouTube industry or in the media industry, and you want to get some suggestions from him.
Right.
But you don't know him, but you know that there is a friend who's a friend of a friend and everything. If you wanted to use logic, how would you make the least amount of phone calls and reach Manu over here? And this is where the beauty of the breadth first search algorithm comes in. Alright. So what you do for breadth first search is that you take this graph tree and you start adding the start element to the list. Alright. You check if Ravi's neighbors have been added to the list. If not, then add them to the list. And also when you're adding them to the list, make sure you set who their parent is. Now this is important. Alright. Now once you've done that, you can remove Ravi from the list because we still have that parent thing going on. Right. Now once you've added that, also make sure that whatever you have added last is not the end that you are looking for. Alright. Okay. So this will go on till the next level, where it starts sort of adds these things. And then at the very next level, what will happen is the neighbor of Lax gets added, which is Manu. And Manu is already at the end. So now that it has been found, it can basically exit the loop. All you need is a handle to the end element. And because now you have set all of the parents everywhere, it will basically have a trace route to the shortest path to the start in this case.
Right.
Yeah. So what I'm showing on the screen is the algorithm as I've taken it from Wikipedia. Whatever we have discussed in the graph images, basically that's just represented as pseudocode. I can leave it here for a minute for anybody to read if they want to. Alright. Now the question is, we're going to be doing this puzzle or
the maze.
Or maze. Yeah, I should probably start calling it a maze. Alright. So I have this maze over here, and how do we represent this maze as as a graph tree? Alright. Now the way to do it is actually not worry about it, but essentially convert this canvas into a block of grids and start finding their neighbors. And once you have found their neighbors, you just add them. You just add them into the graph tree. That's it. Alright. But add them only if the neighbor is accessible. So let's say if you take the first item in the grid over here, you'll see that he only has a right neighbor. He obviously doesn't have top or left, but he also doesn't have a bottom because the bottom is blocked.
Right.
Whereas if you take something like this, for example, he has all 4 neighbors and so on and so forth. Like this guy only has bottom. I think this guy has 2 neighbors, right? You can see that it has 2 neighbors.
Right.
So once you do this, once you just start finding the neighbors and adding them into this graph tree, you don't have to worry about how it is internally represented. Internally, it will be represented as a graph. I think that's all I had to do for an explanation. Let's code it up and see what it looks like.
Absolutely. Let's go.
As per usual, let's begin with a simple setup. I have an index.html file on which is coded a very simple canvas of size 800 by 800. The index also includes a puzzle.js which will serve as our main JavaScript file. The puzzle.js file loads the canvas and fetches the context, the 2D context of the canvas when the window has completely finished loading. It will also call a function called drawPuzzle, on which we will load all of the drawing and looping functions. We'll start by constructing a grid item class. A grid item is located at a specific location and is of a specific size, which is why we need an X, Y, width, and height properties. Each item of the grid will be part of a larger maze, and this is why it needs to either block or allow neighboring cells to be open. I do this using a simple array containing Boolean values. The neighbors are either blocked or opened randomly. I also need variables that can contain the neighboring grid items, a Boolean to see if this grid item has been searched, a parent of this grid, and of course, if the cell should be highlighted. Next, let's write the render function that will draw a line if the neighboring edge is blocked. And finally, we'll highlight the grid if the flag is turned on. Now that we've defined the edges, we'll also need properties that can tell us if the top, right, bottom, or left is blocked. This will be useful when we add the grid items to the graph. Finally, let's also add an add neighbor function that will add other grid items to the current grid item, but only if it is not part of the neighbors array. Let's also add the graph class. This is a simple class that simply contains a list of grid pieces in an items array. It will have a function called addItem that will simply add the parameter to the list of items of the class. Next, we'll add the big breadth first search algorithm. This function takes in two parameters that will be the ID of the grid items that are the start and the end. The job of this function is to find the route from the start to the end. A simple loop is used to find the actual start and end elements of the graph items from the IDs provided. Next, the algorithm is implemented like so, in exactly the way prescribed by the breadth first search algorithm paper. Once that's done, all we have to do is put the found paths into a list and return it. If you remember correctly, this will look like a linked list search. We've come a long way without seeing anything on the screen. Let's fix that. After including the files in the index.html, I'll declare the variables that determine the size of each item of the maze and the number of rows and columns. Finally, we'll need an array for the grid items and an instance of the graph class. Let's start initializing the grid items. We'll loop through the canvas and add a grid item. While doing so, we'll also assign an ID to the grid item. The ID in this case is simply an incrementing number. We'll render the maze by looping through all the grid items and calling its render method. Now that we have completed adding the JavaScript to the index.html file, let's see what the results look like. I think it looks good. Every time I refresh the screen, a new random puzzle is generated. Let's add the grid items to the graph and use the breadth first search to give it a start and end search point and see what it does. Before we start using the breadth first search algorithm, we'll need some utility functions that will fetch us the top, right, bottom, and left neighbors. The top neighbor is pretty simple. The top neighbor is located at the current index minus the number of columns in the maze. While doing so, we'll also have to check for the array bounds as well. The right neighbor is a bit tricky. We'll have to ensure that the index does not exceed the maximum columns of that row. We do it like so. The bottom neighbor is a lot like the top neighbor, except we add the number of columns to the current index and check for bounds as well. The left neighbor is also like the right neighbor. The formulas for those are on the screen. With that being done, we simply have to add the neighbors to all the grid items. We loop through all of the grid items, find their neighbors using the utility functions we just created, and if the neighbors are present, we will add them to the grid item. And finally, let's call the breadth first search algorithm. I'm setting the start as the center of the top row and the end as the center of the bottom row. We'll make the solved path variable global. After finding the solved path, we'll simply set the highlight boolean variable to true of all the items in the solved path. Alright, let's see if that worked. Wow, that worked good. You can see that it finds the path whenever it can. What I mean by that is that if the end is not possible, then none will be visible on the canvas. You can see that for this particular question or for this particular puzzle, there is no solution available, which is why only the end is highlighted. Let me refresh the screen again, and you can see that it sort of looks like a lightning, right? All right. Let's animate the results now and see how that goes. Before we animate, I'll adjust the highlight logic a bit. I'll create an animate function that will loop through the solved path array. Once 0 index is reached, animation is complete. Okay, we finished animating the results and hopefully this works. Oh, there is no solution for this. Let's see. There you can see. You can see that now it animates the result. All right, let's have a look at the results with Ravi. You ready to see the results, Ravi?
Mm-hmm.
All right. Now I've animated it a bit and you can see how the breadth first search algorithm works, and it sort of, so what I've done over here is I've sort of set the start point as the middle of the top row,
right,
and the end as the
middle
as
of the bottom
row. So
right.
This doesn't have to be the case. I mean, if we are going to be uploading this to GitHub, if anybody wants, they can just edit the code so that
the start and end are different.
Look at this, for example. There is no solution for this one because we are randomly generating the puzzle.
Right.
Yeah.
Right.
Yeah. So there you go.
Oh, wow.
There is one more. Right.
Wow.
And so this is not the exact same animation that we saw in the number file video, but it sort of gets close. And people can get creative with this and sort of modify this.
This is absolutely nice.
Yeah. Right. Yeah. It's sort of fascinating to see how it finds the...
Right.
Yeah. So I think what number file had done was like start from, I think, just one point and have, multiple nodes going, and then I'll link I'll put a link to the number file video and we'll see how that goes.
But like you said, they had done it in Mathematica, which we are not really conversant with. This is on JS and Canvas. This looks very nice.
Yeah.
Wow. Very cool.
So I've always assumed that Mathematica was for scientists.
Yeah. It is a paid thing, especially those slightly premium features.
Right.
And I think you need a different kind of education to start using it.
Really?
Even because even the universities normally don't have, only high-end universities with scientific programming, they have I don't know any normal Indian universities which have Wolfram. So, I
pretty
think
interesting.
Yeah, so JS and Canvas is obviously more suitable for our
kind of
audiences.
Work, exactly.
Work. Yeah. So this was cool.
Yeah, this was cool. So there is no episode next week because I'm off to Bangalore.
Maybe you never know. I might do something.
Yeah, I look forward to see what you do. Ravi.
Right. Okay.
All
so
right.
Till then, ciao.
If you have any suggestions, leave a comment below. What we can code up.
Yep.
Tell your friends. Subscribe to this channel. Have fun.
Ciao.